alone in our houses.
All right. Alrighty. Um, so yesterday I got requests that before we start reviewing sequences series to review partial fraction decomp. And I think that's fair because in Unit 2, that's probably one of our more involved integration techniques. So I think it's fair that we start with reviewing that first before we tackle anything else. So keep in mind that I can only do a partial fraction decomp. So my when to use, the only time I'm able to use this in an integral is if I have a rational function and to make it clear what I mean by a rational function, I mean that I could write a function as a fraction with numerator and denominator being polynomials. And the second case I need for me to do partial fraction decomp is I need the rational function to be proper. This has been a while since I used that lingo. Let me refresh what I mean when I say proper. What I mean when I say proper is the highest power in the numerator is smaller than the highest power in the denominator. So highest power in the numerator is smaller than the highest power in denominator. And so one example of the proper rational function will be x plus 2 divided by x squared plus 2x plus 1. I would consider that a proper rational function because the highest power in the denominator is 2 because I have a quadratic in the denominator. Because my numerator is linear, the highest power in the numerator is 1. So I would consider that a proper rational function. So now we tackle how we do PFD. So there are 4 cases of PFD, and it's going to be based off how I factor my denominator. The first case is I factored my denominator as all linear binomials. So denominator can be factored as linear functions. In the first case, that makes it different than case 2 without repeats. And so what happens if that occurs? Well, what I do is I have my linear equation, say A1, A2 for a different one or something, and I keep on going. Could be whatever. And then I have something or some rational or some polynomial in the numerator. What I'm going to try to do So I'm going to set that equal to x plus a1. And the way that I think about the numerator is whatever is in the denominator, what function do I have when I take the derivative? I have a linear function in the denominator. Derivative of a linear function is a constant function. So I have a placeholder constant that I'm calling capital A. And I keep doing that until I exhausted everything that appeared in the denominator. And then what I do is I solve for those constants A, B, C, and so on. That's going to be my main goal. And then once we solve for those constants, we can integrate. So let's go to what happens if I have a linear again. I factor my denominator as linear functions, but I have a repeat going on. So case 2, denominator can be factored as linear functions with repeats. In this case, what I mean by a repeat is I factored out my denominator in the rational function. I have something, and then I have x plus a1 again, keep on going, but somewhere I have a linear function in the denominator being raised by a different power. So like squared, cubed, or so on and so forth. And that's what I mean when I say I repeat. A linear function is being raised by a power. So just like before with case 1, I'm going to set up as normal for all the linear terms that are not repeating. So that's still normal. Let's say a 2 was still normal, and so on. But once I hit to the portion that repeats, let's say I start repeating along the 6th term. Then for the next denominator for G, I'm not going to write down s of k plus 1. I essentially am going to treat the second power and the third power and all of those powers up to the nth power as its own separate denominator. So my next denominator in this scenario will be x plus a of k squared. And I'm going to, and then for my next term, for the denominator, I'm still going until I exhausted to the nth power. So my new denominator will be cubed, not squared, because I repeated. And I keep on doing that and repeat the linear factor that is repeating. Let's say I kept going until S for Scott, until I do x plus a of k, until I reach whatever power that I have. And then my scenario will still be the same. I'm going to try to solve for all of those constants that is appearing. So case 3 is now when it starts to get a little bit a little bit more complicated. Let's say I now factored my denominator. And in my denominator, I have an irreducible quadratic. What I mean with the irreducible quadratic means I can't factor it in a nice way. So cannot factor nicely. So one example of an irreducible quadratic would be something like s squared plus 5. I can't think of a very nice way to factor that in any way, shape, or form without having to do some tricks. That would be nasty. So that's what I mean with irreducible quadratic. And then when you get to case 3, this is when my metaphor for the numerator for the constant will start to come more into play. So again, I have something in the numerator. Let's say I have a linear term. Now let's say that I have an irreducible quadratic term. Just like in cases 1 and 2, I'm going to set it equal to x plus a1. But once I hit the part where I have an irreducible quadratic, I'm not just going to put the constant a in there. My metaphor is still what goes on the numerator. What function would I have if I take the derivative? That's why if I have just linear factors in the denominator, I put a constant up, because derivative of the linear function is a constant function. Derivative of any quadratic function that I could think of is a linear function, which means for my numerator, once I hit the irreducible quadratic portion, I'm going to set up my arbitrary constants. That's right, Anthony, but it's going to be linear. Case 4. Case 4 is the least common because of how nasty it is. And that is if my denominator has an irreducible quadratic there you go. But I have repeats. Meaning in my denominator, so I got my linear stuff going on, dot, 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 whenever. But for my quadratic term that's appearing, my irreducible quadratic, I now have it raised to the nth power for that. So now we ask ourselves, what do we do in that scenario? Well, our dot product is going to be similar to case 2, in which we're going to keep repeating until we exhaust that power n. So I'm going to set I have some linear terms in the denominator, do as I would. But once I hit the repeating quadratic, first time still as normal as I would before. But just like with the repeating linear, every time I'm raising that to a power, I'm treating that as its own individual quadratic term. So instead of moving on, I would write into my new denominator x squared, the same quadratic from before, but now squared. And just like with a linear in my denominator with repeats, I keep going with that pattern. Let's say I ended at x and t. I keep following that pattern until I hit the nth power. And you'll see why I said number 4 is the least common out of partial fraction decomp, because it's very nasty and it's not going to be a fun time if we see that. So that's our PFD in a nutshell. Let's do a practice problem and get us warmed up for today. So here comes the practice problem. And I'm going to split this into 2 parts, mainly because I noticed that on test 2, your partial fraction problem was a 2-part one. And I did like how it was formatted, so I'll keep that format. So part A is saying, use PFD on the following function. 8x minus 15 over 2x plus 1, s squared plus 4. And then part B is integrate, which means evaluate what you got after part A. So I'll give y'all a few minutes to work on that. If y'all have questions, please let me know, and I'll be happy to answer them. All right. I'll scroll this up so it's better on the screen. All right. Work on that for a few minutes. And like I said, let me know if you have questions. keep working on that problem. Just want to make a note. Nick, you found your constants for the partial fraction decomp. Make sure that you let me know, and I'll give you feedback on that. If you're still working, continue working. I just want to get a status report on y'all as to how this problem's going. Okay. Can you message me the what you're getting for your answer so I can double check you? Everyone else, I'll keep on working until about 2 to 3 minutes after 4. So 5 more minutes, and then we'll go to the solution. I'm going to respond to some messages that I have. Continue working on this problem. I'll give you about 2 to 3 more minutes. If you moved on to part A and now working on part B, post your what you get for your antiderivative, and I'll comment on that too. Alrighty. Let's go ahead and start going over the solution. So, as mentioned before, so one thing I want to mention is partial fraction decomposition is going to be the longest part of this type of problem. So let's set this up. Two plus 1, x squared plus 4. So the first thing to ask myself is, what is appearing in my denominator after I factored? I have a linear factor going in there, and I have a quadratic factor that is irreducible, or I can't factor it out nicely. So what that means is I'm going to set first for 2x plus 1. Derivative of a linear function is a constant. So I'm going to put the placeholder capital A on there. For the irreducible quadratic s squared plus 4, because the derivative of a quadratic function is a linear function, it's going to be bx plus c. And so from this, we're now going to solve an equation. So to first kind of see how we can set up the equation, on the right-hand side, I'm going to combine these two rational functions on the right-hand side together as one to kind of make it more clear what I'm going to put or going to set equal. So for a, for the first rational function on the right-hand side, I am missing an x squared plus 4. So that will be a times s squared plus 4 if I decided to multiply and combine them together. Now for the second rational function, I looked and I'm missing a 2x plus 1. And so if I decided to combine the two rational functions on the right-hand side, I'll have to multiply the second one by 2x plus 1. And here's my thought process with that. On both sides of the equation, I'm setting them equal to each other. Both the left-hand side and the right-hand side of that equation, they have the exact same denominator of 2x plus 1 times s squared plus 4. Which means if I want to set these two equals to each other, it suffices for me to show what makes the numerators equal to each other. So, because denominators are the same, I'm now going to say if I want these two sides, these two rational functions on the left and the right-hand side to equal, the numerators must equal to each other. So I want to set the numerator that I started with at the very beginning, 8 minus 13. I'm going to set that equal to a times x squared plus 4 plus bx plus c times 2x plus 1. And so before I do anything, I'm going to do a little bit of work on the right-hand side. And the work that I'm going to do on the right-hand side is I'm going to distribute any terms that I have and multiply anything that I need to. And so I'm going to do that now. Distributing the constant a to the s squared plus 4 will give me a x squared plus 4 times a plus I have two linears being multiplied together, so I'm going to FOIL them. If I do that, I'm going to get, for first term, 2 times b x squared, plus, for outer, I'll get b times x. Inner, I'll get 2 times c times x. Last, I'll get c. And now what I'm going to do is I'm going to combine like terms together. So for example, the two that I underlined in pink, they both have a quadratic term of s squared. So I'm going to combine them together. The terms that I underlined in blue, they have a common factor x together, so they're getting grouped together. And for the two that I underlined in orange, they don't have a variable x in them, so those are constants with respect to x, so I'll group it together, giving me, for my final factoring the left-hand of the right-hand side, a plus 2b. They both had a common factor of x squared, so I factor out the x squared. Next, I'm going to group the terms that have an x with them. Since the common factor is an x, I factor out an x to give me b plus 2c times x. And now for the constant, I'm going to group those together to give me 4a plus c. And my thought process with that is the following. And to make it more clear, I'll include 0 plus s squared over there. Here's what I want to do. If I claim the left-hand side and the right-hand side are equal, then the coefficient on the left-hand side that is married with x squared must equal to the coefficient on the right-hand side that is married with x squared. Same thing for the linear term of x. Same thing for the constant term of x. And so now there are two ways that we're going to solve for x. Fourier's problem, do it in both ways. I want to do it the first way since I have it geared up and set up for the first way, and that is do a linear system. Now the reason why I had to factor this way is this will help me set up a linear system. My linear system will be 0 equals a plus 2b. It equals b plus 2c. Negative 13 equals 4a plus c. And essentially now I have a linear system of 3 equations and 3 unknowns. So I'm going to use my tools from algebra to solve for that. And my rule of thumb for any linear system, get some load-bearing fruit. In this case, my load-bearing fruit is the first equation because I have the left-hand side 0, a plus 2b. So if I subtracted both sides by 2 times b, I quickly get that a equals negative 2b. Which means anywhere that I saw an a in any of the other 2 equations, I can now substitute that in for a. For this case, in the third equation, because I have 4 times a, I replace it with negative 8 times b plus c. So now let's modify what equations are left. 8 equals -8, or nope, b plus 2c. And -13 equals -8 b plus c. And here now I have just two linear systems with two unknowns. I can now use elimination in order to solve for one of them. Doesn't matter whether or not I eliminate C or I eliminate B. For a yes scenario, I will eliminate C. So for me to eliminate C, I'm going to multiply the whole second system of equations by -2, and then I'm going to add both of them together. So if I do that, I will transform my system into the following system. I've done nothing to the first equation, but to the second system, I now have 26 equals positive 16b minus 2c. And now I add 2c plus -2c. Those are gone now. 16 plus 1, that gives me 17b. And 26 plus 8, that gives me 34. Now all I gotta do is solve for b by dividing by 17. So that means after dividing by 17, I get my final solution that b is equal to 2. And with method 1, once you know one value in that system, I say that you win and you can reap the profits from your hard work. Because if I now know that b equals 2, now that is known information, and I could solve for the other two constants. In this case, I could quickly solve for a, because I concluded before that a equals -2 times whatever b is. So a equals, we concluded before that equals to -2 times b, but I now know what b is. B is now +2, which means a is now -4. And now I can solve for c by either plugging in 2 in the second equation or -4 in the third equation. For this case, I'm going to go ahead and solve for c by plugging 2 in to the second equation. So I have 8 equals 2 plus 2c. If I subtracted both sides by 2, I get that 6 is equal to 2c. And then if I divide it by 2, I get that c equals to 3. And so there's method 1 of how to solve for that using our system of linear equations. And for reference, for the second part, or the second way to show yes, I'm going to have what we solved for our constants up above, so we could go back to it and make sure that we're correct. Well, let's say you don't like to do set up a linear system and solve for it. Let's talk about method 2. That is plugging in values for x. A, B, and C are my unknowns, not x, so that's what I'm trying to solve. So for yes method, I'm going to copy down the equation that we had by setting the numerators equal to each other prior to expanding upon that. So here's back to my equation for the numerator before I factored. Now, my thought process is I'm going to plug in a value for x that will make something with the other unknowns equal to 0. So that way I'm only left with one unknown, and I can solve for that very quickly. And the quickest way to show that is find out what makes something equal to 0. In this case, I have 2x plus 1. If I plug in -1/2, that term's going to go to 0, which means I will have b times -1/2 plus c times 0, which means this whole thing will equal 0. And I'll only be left with one unknown, which will be a. And so let's do that. I plug in -1/2. I get 8 times -1/2 minus 13 equals a -1/2 squared plus 4 plus b times -1/2 plus c times 2 times -1/2 plus 1, which we already concluded that gives me 0, which means this whole second term is equal to 0. So on the right-hand side, I'm just left with a times -1/2 squared plus 4. -1/2 squared is 1/4. 4 can be written as 16/4. So I have for my constant 17/4. On the left-hand side, 8 times -1/2, that's -4, minus 13, I have -17. And now when I solve, I'm just going to multiply both sides of that equation by 4/17 to cancel out. So the 17's are cancel out, and I get the conclusion that -4 is equal to a, which means that I'm 1 and 3 now. If we concluded in method 1 that a also equals -4. So that means I'm on the right trail. So with this method of plugging in values that we don't know, note that it might be harder now because x squared plus 4, that's still a little bit harder to figure out what makes that 0. ES plus C, there's no way to know that unless you know what B and C are. So here's how I could go about that. And I'll pull that equation back up. A is now known. No, A is -4. So that means I'm not treating A as an unknown anymore. I'm now treating that to figure that out. Yes, Unique, this is the alternative way. Method 1 was doing a linear system. But I see that B is multiplied by X, which means if I plug in 0, that tells me that I want to have B times 0 and plus C. I get rid of one of my two unknowns left, and I'm just left with one unknown, which is C. And so now let's do that. So plugging in 0, I get 8 multiplied by 0 minus 13 equals a 0 plus 4 plus b times 0 plus c, 2 times 0 plus 1. So after simplifying, I'm only left with negative 13 on the left-hand side. I already know that a is negative 4, so I can use that now to get that after simplifying, I have negative 16. B times 0 is 0. 2 times 0 is 0. So after simplifying, I'm just left with, on the right-hand side, negative 16 plus c. Meaning, once I add 16 to both sides, I'll have 16 negative 13 plus 16, or 3 equals c. So I'm now 2 for 2. So now for the third part. Well, now I have one unknown left, so it doesn't matter what I plug in for x. So in that case, I'm just plugging in the easiest one that I could think of that does not eliminate b, which will be 1. So 8 times 1 minus 13 equals, I already now know that a is negative 4, so I'm using that now, times 1 plus 4 plus b times 1 plus c, which I now know is equal to 3, and I use that now, times 2 times 1 plus 1. And now let's simplify that as much as we can. 8 times 1 is 8. 8 minus 13 is a negative 5. 1 plus 4 is 5. Times negative 4 gives me a negative 20. So for the second term, I still have b plus 3, and then 2 times 1 gives me 3. And I'll distribute that 3. Well, that should be 3. IB. I know that c is 3 now. So I use that. Now I distribute that 3 that I got from adding 2 plus 1. You give me negative 5 equals negative 20 plus 3 times b plus 9. And now I combine like terms. Negative 20 plus 9 is negative 11. Negative 11 plus 3b equals negative 5, which I'll write down now. Add both sides by negative 11 by 11. I'll get 6 equals 3b. Then dividing by 3, I conclude that 2 equals b. And now I'm 3 for 3, and I got the same answer that I did with method 1. So I still concluded that a is negative 4, b equals 2, c equals 3. Before we move on to part B, I'll give y'all a minute to write that down. And if y'all have questions, let me know. All right. So now we integrate and we do part B. because of part A, I can now rewrite my integrand as, I know that A equals -4, B equals 2, and C equals 3. So I can now replace my integrand as -4 over 2x plus 1 plus 2x plus 3 over x squared plus 4 dx. Integrals are linear, so I have an addition between the two rationals on the right-hand side. So I can use my property of integrals that says, take the integral of the first term, take the integral of the second term, join them together by addition or subtraction. All right, and let's see how we can do that. So I say for the first integral, I say that we win automatically because the derivative of 2x plus 1 is 2, which means I could do a u sub to quickly get that derivative. And for the u, I can rewrite -4 as -2 factored, and then the 2 inside the integral. So that way, if you want to do the u sub, you can do that very quickly, with u being 2x plus 1, du being 2 times dx. And what you get back with respect to x is we'll have -2 times the natural log of the absolute value of 2x plus 1. Well, that's nice. We have one integral taken care of. We still have a second integral that we need to get. So let's talk about the second integral. The first thing that I'm noting about that second integral is I have a common denominator of x squared plus 4. So I could break that integral down as, first, copy down what I already know. And now for the second integral, because I'm dividing by a common denominator of x squared plus 4, I can split this up as 2x divided by x squared plus 4 plus 3 divided by x squared plus 4 dx. Just like before, integrals are linear, and I have an addition going on in there. So I can use the property of integral that says, take the integral of the first term, take the integral of the second term, join them together by addition. So I get the knowledge that I currently have plus the integral of 2x plus x squared plus 4 dx plus the integral of 3 divided by x squared plus 4 dx. And so let's talk about those two integrals separately. First, let's talk about the first integral. How would I tackle that integral? Or how would I solve for that if that was by itself? Give you a minute to type your response or let me know. Bingo. Thanks, Anthony. Remember that du, it'll be 2 times x times dx because it's technically differential. But besides that, you're Gucci. So I would do a u sub again. Because derivative of x squared plus 4 is 2 times x. So I can do a u sub. For u is x squared plus 4. Let's make that a clearer 4. And its derivative is 2x d of x. So that's a 1 over u du. Natural log of absolute value for u. And then rewrite in terms of x. Because that's an indefinite integral, I'll include a plus c. So that integral is taken care of. Now let's move on to the second integral. This one's a little bit more challenging than the second integral, but I say we can still tackle it. Here's how. First, I'm going to take the 3 out to give me 1 over x squared plus, and I'll go ahead and write out 4 as 2 out. Now I agree, it's going to be arctan. And in particular, the antiderivative rule that I'm thinking of, this is one that we haven't used in a while. If we just had x squared plus 1, we know that that's arctan off the bat. But if it's another constant squared, then for arctan, its antiderivative is 1 over that constant a times arctangent of x over a plus c, where in this case, a is equal to 2. If you don't remember that antiderivative rule, you can always think of a u sub once I factor out 4 or 2 squared out, and then my u will be x over 2. But using that antiderivative rule, I get that my integral is 3/2 times arctan 3 over 3 of x over 2, not 3/2, plus c. And now the final integral is taken care of. So I say I'm now finished. So I can use my therefore symbol or my lazy triforce symbol to conclude that the integral of 8x minus 13 divided by 2x plus 1 times x squared plus 4 dx equals the natural log -2 times the natural log absolute value of 2x plus 1 plus natural log absolute value x squared plus 4 plus 3/2 arctangent of x over 2 plus c. And that is a very long problem to do, but that will finish our problem. To give you context, Jake, I chose that problem from fall 2018 test 2. Keep in mind that for this integral, or for partial fraction decomp, you don't have to do both method 1 or method 2. Setting up the linear system or plugging in values for x, you don't have to do both of them. Pick the one that you like the most, and that will be how you would tackle that problem. So I'm going to take a minute to sip my water. I will pull that back out so y'all have the answer. If y'all have a question about that example or that problem, please let me know and I'll be happy to answer. And also, there's a reason why I wanted to talk about partial fraction before series and sequences, because I think from Unit 2, this is kind of the one of the nastier ones to talk about. Oh gosh. I don't know about Encore, Isaac, because I didn't want to have y'all do some practice problems on sequences and series, mainly on series test. Mainly because Dr. Burr has let us know now that Unit 3 will cover 50% of the final. So I want us to get our hands dirty on that. Alrighty. In that case, we'll move on to reviewing sequences and series. And for this one, this is doing a lot more hands-on, because I think the best way to learn sequences and series is to do a lot of problems for you. So what I'm going to do is kind of just do a quick recap of all the tests that we have, so that way we're all on the same page with the current tests that we have for convergence and divergence of series. So and for a nice summary of when to use the specific test, I want to reference my session 10.8 lecture notes. That's kind of a nice summary on how to use, when to use which test for a series. Kind of what I'm going to do is give you all a lot of problems and kind of do a quick recap on specific methods on series. So for the rest of this review, I'm giving you all a lot of series, and all I'm asking, does it converge or does it diverge? So the first method, or the first problem to give y'all, is this following series. I want to know whether or not this series is convergent or divergent. Natural log of I divided by I plus 1. I'll give y'all a few minutes to work on that before we go to the solution. And if y'all have questions, again, please let me know. give you all about 2 to 3 more minutes to work on it. If you're stuck with how to begin, I'll give you all a hint. And my hint is it possible to rewrite that? All right, like I said, I'll give you about 2 to 3 more minutes to work on it before we go over the solution. I agree, Nick. Now tell me, now go and conclude whether or not it converges or diverges. Alrighty. Let's go over the solution. So as Unique mentioned, we're going to have to do a telescoping series because I can rewrite my series natural log of I divided by I plus 1 as, because I have a quotient inside the natural log, as natural log of I minus, I should stay in pink, minus natural log of I plus 1. And so the reason why this is a telescoping series is because, or what we have to do for telescoping, is I have a difference of two terms that is appearing. So that's one thing that tells me I have to do a telescoping series. I have a difference of two terms appearing within my series, and the distance between each term is a set constant. Between each part of the terms is constant. So here's what's going on if I want to do telescoping series. We don't put it on that little chart for convergence test. And that's mainly because if we have to use telescoping series, we're actually using the definition of a convergence series for YITS. And so let me write that down. Telescoping series uses the definition of series. And what that is that a series, an infinite series that I'm going to call X, is equal to the limit of its partial sums. And so what we do with a telescoping series, I want to know what the partial sum looks like, and then I'm going to take a limit. So let's check what goes on with x of n. So before we do that, let's kind of extrapolate a little bit, and let's just say we start off with the second partial sum. Well, second partial sum, that sum from 1 equals 2. If I do that, well, I equals 1. So 1 minus natural log of 1 plus 1 plus natural log of 2 minus natural log of 3. And that is what I get when I equals 1, when I equals 2. And what I'm checking for is if any of those terms, any parts within those terms cancel out. In this case, nothing has canceled out yet. So I can't see a pattern for what the nth partial sum would be. So let's continue on and let's do the third partial sum. So now I'm going to continue on until I hit I equals 3. And I'll keep it like that. When I equals 3, natural log of I, so 3. Natural log of I plus 1, so natural log of 4. And I'll go ahead and change that to natural log of 2. This is what I get when I equals 3. And here I can begin to see some cancellation. Oh, I was able to see some cancellation in the previous term. I have a minus natural log of 2 and a plus natural log of 2. So those are gone now. I have a minus natural log of 3, a plus natural log of 3. Those are gone now. So when I have the third partial sum, only 2 of them are remaining, the natural log of 1 minus natural log of 4, or natural log of the index that is with I plus 1, which in this case is the third partial sum. So that will be 3. And to keep that relation, I'll rewrite 3 in light blue. That seems to be my pattern. Let's see if that's observed again with the fourth partial sum. So now I'm going to add what I get when I equals 4. So natural log of 4 minus natural log of 5. That is what I get when I plug 5 into I. And now I have a minus natural log of 4 plus natural log of 4. So they're gone. And so the survivors are the natural log of 1 minus the natural log of 5, or that should be I equals 4. I cannot read. Or natural log of 4 plus 1. Now it seems like the general pattern is for whatever n is for the nth partial sum, what will be surviving is the natural log of 1 term, which is 0, minus natural log whatever subscript I have for n plus 1. And that seems to be the pattern that I'm following going along with that. So now I'm going to begin to extrapolate. And now I'm going to conclude for my nth partial sum that if I continue on with that pattern, let's say I plugged in n minus 1, and then I plugged in n for I, we concluded before that anything, unless the very last part, will die off. And natural log of the subscript with the partial sum plus 1 will survive. Meaning, I'm going to conclude that my nth partial sum for a series is natural log of 1 minus natural log of n plus 1. I could go a little bit further because natural log of 1 is just a fancy way of writing 0. So my nth partial sum is negative the natural log of n plus 1. Now that I have the nth partial sum, I can now say, by definition, the limit of my infinite series, what we had at the very beginning, is equal to the limit of my partial sum. I did all of this work to conclude that my partial sum as limit, not natural log, and going to infinity of negative times natural log of n plus 1. So I'll put that negative up front because it's a constant. I'm taking, there we go, natural log of n plus 1. I'm taking an infinite limit of natural log. That's an in behavior type relationship. The natural log part equals infinity And because of that negative sign up front, I have negative infinity for that. So because my limit of partial sums equals positive or negative infinity, that means my entire series is going to diverge. So my conclusion is therefore the series sum from I going from 1 to infinity of natural log of I over I plus 1, I concluded that that diverges. And if you had to justify why, by definition, because I said by definition of a series, I show that yes diverges. Give y'all a minute to catch up if you're writing on your home. If you have a question, please let me know right now.
Do you know how the test is going to be laid out yet? I know you had that meeting with her yesterday.
So mainly all I know is, I mainly know is 50% is the unit 3 stuff.
Mm-hmm.
Not a MATLAB exam unique. MyLab math. If we do a MATLAB exam, that's gonna be fun for everybody. Yeah, so half of it will be sequences and series and power series.
Oh boy.
I think that's kind of fair because we didn't have a test 3, so
Yeah, that makes sense.
I kind of agree with her on that. 20% is on parametric and polar equations.
Oh boy.
30% is on everything else that we learned pre-quarantine.
Okay.
As for layout, I feel like one thing that'll be similar is if you go on MyLab Math, you could do practice tests on the study plan portion, and it's going to be very similar to that format. So I'll write that down. Practice test, and I think that's under study plan.
And what is that?
It's on MyLab Math. It essentially gives you like quizzes and stuff.
Okay.
Formed by MyLab Math, and it's going to be that format. From what I looked, it seems like it's a fill in the blank and it's fill in the blank and multiple choice mainly. So it looks like it's not going to be a free response type of scenario. It'll be
fill in the blank as what? Like you click it and there's like options that you can choose?
You do the work on your side and you input your answer.
Okay.
So like you do the little scratch work on your desk and you type in your answer.
Okay, that one gets scary.
Yeah, well, like I said, we're trying our best to make the growing pains not that.
Okay. Should we, if we do, I don't know like how it's gonna work, like when it's gonna tell you what your answer is, but like if we like put in something that is the right answer, but it's just not formatted correctly, should we like take a picture of that and send that to you?
You can if you want to. I would say do that, and then I could talk to Dr. Burr to see what her final decision will be.
Okay.
I feel like that'll be safer. Just note that if you do that, Anthony, I will have to go through Dr. Burr because she'll be the final person.
Yeah, no, that makes sense.
Jake, I see your question. I can't specify the number of questions you can see. All I can specify is kind of how the material is laid out. So 50% on sequences and series in power series, 30% in the final on stuff we saw before quarantine, So the applications of integration and integration techniques, and 20% on the parametric and polar equations. I can't quite give a specific number of questions. All I could say is kind of the distribution of material. I don't know if that helped your question, but like I said, I can't give a specific number. Any other questions since we brought this up? All right. Well, like I said, since half of the final will be on sequences and series and power series, let's get to it and let's start practicing more. But before I move on, does anyone have any questions about the problem that we just worked on? Or if you do have a question about the final, I could try to answer that as well again. Nope. To answer your question, Matthew, no. You should be good to go. So to answer your question is, you don't have to do anything for your end. You're good to go. Alrighty. Let's try this out. Another serious question. Okay. Good one. There we go. So next problem. Show whether or not yes sequence or yes series converges or diverges. So 2n plus 1 raised to the nth power divided by n to the 2n power. Give y'all about 5 minutes to work on it, 7 minutes to work on that. And if y'all have a question about it, please let me know. Alrighty. So before I start out with the solution, what tests do you think I should use in order to check for convergence or divergence of the series? All right. So Anthony says root test. Anyone else? All right. So I do agree that I will have to use the root test on it. So before I go on, let's do a quick recap of the root test. So what root test says is, oh, there we go, is for my series, I'm going to define L as the limit as my terms go to infinity of the kth root of the absolute value of what appears inside of the series. One thing that I prefer to write that as, instead of the kth root that you see in a lot of Cal books, I prefer to be read it as d1 over kth power. And so based on what that value L you get, you can conclude three things. You conclude convergence of the series if L is strictly less than 1. You can conclude that the series is divergent if L is strictly greater than 1, and if you have that L is equal to 1, I'm inconclusive. Meaning I can't tell you anything about the convergence or divergence of the series. All I know is that I converge. Or I don't know nothing, which means I have to try another test. And with root tests, I don't just get to say convergence. With root and the ratio tests, those two tests are very powerful in the sense that if I have that the series converges by this test, I'm absolutely convergent. So let's try that out with the series that we have before us. So I want to have L. I want to define that as the limit as k goes to infinity of the nth root of what's going on. So my nth root so for my terms, I have 2n plus 1, all of that to the nth power, divided by n to the 2n power, absolute value 1 over n. Now, everything inside the absolute value is positive, which means that the absolute value is redundant. I can rewrite that needs to be n, not k. I can rewrite as the limit as n goes to infinity of 2n plus 1 to the nth power divided by n squared n to the 1 over n. And now here comes when I prefer to use the root test. I would prefer to use the root test if the terms in my series are being raised by the index of my series. So in this case, the reason why I would want to prefer to use the root test is because the terms in my series, both the numerator and denominator, are being raised by the nth power. Meaning, I can rewrite everything inside the bracket as follows. I can rewrite as 2n plus 1 over n squared raised to the nth power raised again by 1 over n. I have something being raised by a power, being raised by another power. So I can use my property of powers to say the powers n and 1 over n just get multiplied together. But n times 1 over n just gives me 1. I am just left with the limit as n goes to infinity of 2n plus 1 over n squared. Now I have a rational function. My numerator is linear. My denominator is quadratic. Highest power of the denominator is greater than the highest power of the numerator. So that equals 0. And I don't know about y'all, 0 is definitely less than 1. So now I can write my conclusion. Since L equals 0, which is strictly less than 1, by the root test, the series sum from n equals 1 to infinity of 2n plus 1 to the n divided by n to the 2n power converges. And if I want to specify absolutely or just normal convergence, since I did the root test, if I have convergence, then it's absolutely convergent. So, any questions about this problem before we move on?
So as long as it converges by the root test or the ratio test, it converges then absolutely.
Yep, and that's the power about those two tests, is that if I have convergence via the root or the ratio test, it is absolutely convergent, not
Okay,
just
and
convergent.
that's how you're going to be able to tell every time, is you then put it into the root/ratio test.
Right. That's why I didn't have to do by definition of absolute convergence, because I already have it.
Nice.
Yep, and that's a really good question to ask, is when to check for absolute and conditional. So before we go on to the next example, I do want to discuss that, because that is one valid question to have. Is my convergence absolute convergence or conditional? So let's recall. If I have a series that's convergent, I say that the series is absolutely convergent. And the definition that we have to check absolute convergence is if I take the absolute value of each term in my series and I check again that the series is convergent, then I can now say further that the series is absolutely convergent. The other type of convergence that I have is conditionally convergent. And I get conditionally convergence if I check whether or not the series, where I take the absolute value of each term, I actually showed that is a divergent series. I say that my original series is conditionally convergent because while the series is convergent, if I take the absolute value of each term to make them all positive, I actually get a divergent series. And that typically comes up when we're doing alternating series tests, because I could get a series where I actually have that the absolute value is divergent. And so with that, that brings us to our next example. And this one I'm going to do because this is one of the times where it seems weird before you see someone do it. And that is to check whether or not this series converge or diverge, and also check if it's absolutely or conditionally convergent. So sadly, I can't do, it's going to be difficult for me to use any of the tests that I know right now. Limit comparison, it's going to be hard to find a function to compare it with that I know it converges or diverge. Alternating series, it's not quite an alternating series because for sine of 2n, I could be that. So what I'm actually thinking of doing, Isaac, is similar to squeeze theorem. If it was a sequence, I would definitely go to squeeze theorem. But now we're dealing with a series. So here's kind of my idea for the solution. If I have that sine term and if it's hard for me to tackle, let's consider the series where I take the absolute value of that whole thing. And here's why I want to know that. And here's kind of my thought process for you. And it's a property of absolutely convergent series. So because it is a property, I'm going to list this as a fact. And the fact is that if I know that a series is absolutely convergent, if I already know that by fact, if the series is absolutely convergent, then that implies the series overall is convergent. And so let's rewrite that fact again, kind of make sense of what that means in a nutshell.
Shouldn't there be an absolute value sign over the first A of K?
Say that again, Anthony.
Shouldn't there be an absolute value sign over the first A of K for the absolutely convergent?
Oh, that's what I'm going to rewrite about. I just wrote down as absolutely convergent, and I'm just rewriting what that fact represents in series.
Okay.
You're exactly right. So, and what Anthony was kind of pointing out was, since I have that I know is absolutely convergent, then I know this series with the absolute value is convergent. And that's by definition of an absolutely convergent series. So I know that this series is convergent. What the fact is saying is, if I know that this series where I take the absolute value of every term is convergent, that implies that the series where I remove the absolute value converges. So one strategy of showing convergence or divergence of a series, if it's difficult to observe, like with this with sine, try to check convergence or divergence of the series where I take the absolute value of each term. If that's the case, then I say, oh, well, my series is absolutely convergent, which means that the original series is convergent. So that's what I'm going to try to show. Is I'm going to take the series with the terms being absolute value, and I'm going to check if that series converge. And I say it does, and I'm actually going to use a method that we mentioned before, but it's kind of one of the things that I said. You'll probably choose the other one in terms of yes, and that's direct comparison test. And here's why. So right now my terms are sine of 2n plus 1 over 2 of n. My denominator is already positive, so the absolute value is redundant. Actually, let's add this here as a middle step. The denominator is always positive, so the absolute value is redundant. So I have sine of 2n in the absolute value divided by 1 plus 2 to the n without the absolute value, because pick whatever value positive number n I can think of, my denominator will be positive. Now for that sine, well, I know that sine, regardless of what my input is for sine, is between -1 and 1, which implies the absolute value of sine will always be less than or equal to 1. So that's going to be less than or equal to 1 divided by 1 plus 2 to the nth power. And in terms of my direct comparison test, here's my terms of the series that I want to check convergence or divergence of. And here is the terms of the series that I want to compare with. So direct comparison means I have less than or equal to. So because I have the less than or equal to, I need to now check whether or not this series with 1 over 1 plus 2 to the nth power converges. Because I have the less than or equal to. So that's my next step. I want to check if that series is a convergent series. And so let's double check that. So here, what test would I want to use to check if the series with the terms 1 over 1 plus 2 to the nth power converge? Ratio will actually be a little bit difficult because I have 1 plus 2 to the nth power. So that means when I do the setting up the L, I'll have 1 plus 2 to the n plus 1 power over 1 plus 2 to the nth power. So I'll have an indeterminate form, which is how we do in a good bit of L'Hopital's rule. I'm actually thinking of an easier way to tackle that. You could do ratio if you want to, but I'm actually thinking of something easier. Here's what I'm thinking of. And you could do this either one or two ways. It's going to be a comparison test again. And here's why. My thought process in general when choosing a comparison test is if I have an algebraic function, let's write that better. Or similar to a geometric series. And for this particular problem, I want to do a comparison test because of the latter. Because I have 2 to the n power in my denominator, which looks very similar to the geometric series 1/2 all of that raised to the nth power, or 1 over 2 to the nth power. So I want to compare this series with 1 over 2 to the nth power. You could do direct comparison test, which I'll do here, but you can also do limit comparison test. So let's show why I can do direct comparison. Two to the nth power is a positive number. Adding a positive number with another positive number will give me that inequality, irregardless. Dividing both sides by 1 plus 2 to the nth power and dividing both sides by 2 to the nth power, I get 1 over 1 plus 2 to the nth power is less than 1 over 2 to the nth power. So there's my B of n. Here's now my C of n. I'm not going to use B of n again because I already used that with 1 plus 2 to the nth power. And with this series, 1 over 2 to the n, 1 over 2 to the n, that's 1/2 to the nth power. And that's a geometric series with r be 1/2. Which is less than 1. Which means by geometric series, the series that I'm comparing with converges, meaning that the series I want to test converges. Oop. Let me go ahead and plug in my tablet before it dies on me. That will be awkward for everybody if it just died during a meeting. There we go. So, because one of the series with terms 1/2 to need to converge, I have that, let's stick with blue. So by direct comparison test, the series 1/1 plus 2 to the nth power converges So I now know that this series is convergent by direct comparison test. Now going back up to here, I now check that the series with terms b of n, 1/1 plus 2 to the nth power, converges, which means by direct comparison test, the series that I wanted to test in the very beginning is also convergent. So I'm going to write that down. Thus, by direct comparison test again, and I'll put a little sigh for using it twice. By using it again, I conclude that the sum from n equals 1 to infinity of the absolute value of sine to the 2n power divided by 1 plus 2 to the nth power, I concluded that converges and by that remark from above, I now have my final conclusion about the original series, which is sum with everything with absolute value converge. My original series converge. Jake, I see your comment. I'll answer that once I'm done here. Converges. Absolutely. To answer your question, Jake, the reason why I want to put the absolute value with the original series is based on the original series that I have, I can't think of a good way to test it using one of our tests. I can't think of alternating series. That's not going to work because I can't rewrite sine of 2n as always being -1 raised to the nth power. Comparison test, again, because of the sine, I could accidentally pick a series to compare with that could be convergent or it could be divergent. That sine is too sensitive. So because of that sine of 2n term, it makes testing with my normal methods to be a little too hard. So that's why I'm taking it with the absolute value. So why the absolute value part? My main observation why is because regardless of whatever is inside the sign function is always bounded between -1 and 1, which means the absolute value of sign is strictly less than 1. Meaning, way back in, let's pull that up, way back in this step, I could quickly do a direct comparison because I've done nothing to alter the denominator. I've only altered the numerator, which is why I have less than or equal to. And overall, why I'm checking that the absolute value of the series converge is because what I'm going to show is that my series with gets converges. And if I showed that the series with the absolute value converge, then I get that the original series converges for free. So that's why it's important for me to put the absolute value. I can't think of a clever way to tackle that series before the absolute value. So I'm going to resort to take the absolute value of each term, which will give me that for free. You're welcome. And the best way to summarize that inequality is absolute convergence implies convergence. Meaning that if you have an absolutely convergent series, you also have a convergent series. All right. I apologize for keeping y'all 19 minutes after 5:30 p.m. Eastern Standard Time. But I think that's an example that it seems very weird when you first see it. So I want to make sure that we talk about that one, at least before the final. I guess before we end this meeting, any general questions for me that y'all have?
I'm gonna head out. See you, Scooter.
All righty, see ya.
Thank you. Have a good one.
I got a nice dinner waiting for me.
What you making?
Burritos.
Nice.
Well, they've been done for an hour, but I'm going to eat them now.
Nice. You enjoy.
Yeah.
Thanks, Dr. Scooter. Have a good one.
You too. All right. I'll go ahead and end the meeting. If y'all have any questions for me, make sure that you send an email to me, and I'll try to answer that as quickly as I can. All right. I will see y'all later.